Hello, y'all. Welcome to lesson 117 in my DP chemistry curriculum. Today we're going over structure 3.2.2. Functional groups give characteristic physical and chemical properties to a compound. Organic compounds are divided into classes according to the functional groups present in their molecules. We will be able to identify the following functional groups by name and structure: halogeno, hydroxy, carbonyl, carboxyl, alkoxy, amino, amido, ester, and phenol. Now, this is probably one of the hardest units in organic chemistry and in chemistry that students find because to understand, you need to memorize all these functional groups, how to name them, how to recognize them. So, as I go through this, every once in a while, I will attempt to make a flashcard. And my suggestion to you is, as a student, make sure you pause on this and go ahead and make this flashcard. I will divide it up as this. One side might be like this, front, and back. Anytime I do one of these, it is going to be beneficial for you to make a flashcard doing exactly what I did here. And this way you can study these throughout because it's one of the best ways to memorize. Otherwise, you can make a Quizlet or whatever, but it will help. And honestly, I believe physical flashcards might be the best for this. You can take them anywhere and learn them anywhere. So, my big suggestion is make flashcards. Memorizing this stuff is going to make the entire organic chemistry unit easier by a mile. Please, please, please make sure you do this. It is required of you to understand these and have them memorized for your DP exam. With that said, let's jump right into it. What the heck are functional groups in these classifications? Well, like we said earlier, organic compounds are classified by functional groups. Now, I mentioned in the last unit a functional group and kind of what that is. I'm going to be shortening it to FG for the remainder of this video, but a functional group is nothing but a group of atoms that give an organic molecule its physical and chemical properties. So why do certain organic compounds act the way they do? Well, let's do their functional groups. Generally, what we say is if we have the same functional group, that refers to the same, and another term we'll use is class of organic compounds. And if they're in the same class, then they have similar properties. I don't say same here because each compound is slightly different. It could be the length of the hydrocarbons, could be the number of functional groups or the types, but overall, we will just say similar properties based on that functional group. So, a good example might be looking at this series. Keep it in red. So, in this case, here's our first one, here's our second one. I'm going to try and draw skeletal formulas most of the time, but in the beginning, I'll start with full structural formulas just to help out a little bit. So what you'll notice here is that most of this is the same. Carbon with some hydrogens and an OH. Carbon, carbon, some hydrogens, and then an OH. Carbon, 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 hydrogens, and an OH. The OH here is the functional group. We'll notice that they all have single bond OH. This is what we would generally classify as the hydroxyls, sometimes also hydroxy. You may recognize that from the term hydroxide, which is OH minus. Now, we commonly refer to this as alcohol, commonly refer to as alcohols. That is a common name for the hydroxy functional group. And so we can actually note that all three of these compounds will act similarly in some respect because they have the same functional group and have the same class. So with that said, let's just start jumping into all the different functional groups. The first thing we're going to do is separate out the hydrocarbons. Hydrocarbons. As the name implies, hydrocarbons are composed of carbon and hydrogen. We discussed this in our combustion unit when we talked about combustion of hydrocarbons, but we actually have three classes of hydrocarbons. We have alkanes. Alkanes are what we refer to as saturated. What that means is that there are all single bonds. So every carbon is bonded with a single bond. And I'm going to do some examples of this momentarily, but this is actually where we will do our first flashcard. So all single bonds. We're going to put that on one side of our flashcard, and on the other side, that is alkane. And we reference alkanes with a suffix, ane. And again, I will be a little more clear in that after we go through all of these. Well, you know what? No, let's just do this right now. So an example might be carbon, single bond to carbon. We'll notice this is saturated. We could not add one more hydrogen to this. There's nowhere to add it. We can't break any bonds to add more hydrogen. Otherwise, it becomes something fully different. We call this ethane. You'll notice the suffix ane. So this is an alkane. All right, moving on to our other type of hydrocarbons, alkene. Alkenes. These have one or more double bonds. And we will replicate our note card here. What I might just do before I fully finish this is copy this so that I can just start pasting. All right. Now, an alkene might be one or more double bonds on the first side. We call that an alkene, suffix ene. So make sure you are making these note cards. In our example right here, again, I'll use two carbons and I will call this ethene. Again, we have that ene suffix now. You'll notice a couple things. As we do this, this bond could theoretically break. The difference between ethene and ethane is ethane has more hydrogens. We would refer to ethene as unsaturated. If you think about oils and fats, you may have heard of unsaturated and saturated fats. They're actually referring to the structure of the carbon chain, whether or not there are enough hydrogens. Now, one other big difference is our bond angle is 120 degrees now, as opposed to our original 109.5 degrees. So it's very important to keep track of these changes. In fact, it won't be exactly 120. There's a higher electron density, so it will be around 120, a little bigger on these, and a little smaller right here, but it's still trigonal planar. The last one here is alkynes. If you are good at patterns, you may recognize single bonds, double bonds. This is one or more triple bond. And so our flashcard is going to read something similar, one or more triple bond. That is called an alkyne with a Y and E. And you may even be able to guess the suffix, ine, Y-N-E. Our example here will be carbon with one hydrogen on each side and ethine. So you may start seeing the pattern on how we name these here. And so that is our alkyne. So before we go any further, you may be asking me, well, how do you know that it's F, F, F? Because I've heard of compounds like methane, I've heard of maybe ethane, or further up we drew ethanol, methanol, propanol. So where do these names come from? Well, before we go any further, when we're talking about carbon chains, we actually need to learn some carbon prefixes. Carbon chain prefixes. Now, for this one, I'm going to be a little bit extra with this. And I'm going to do 5 note cards at once because I'm a little lazy. I'm going to do that twice. Oops. Two, three, four, five, two, three, four, five. So these are all going to be front and then back. And so if our carbon chain is 1 carbon, we use the prefix meth. If it's 2 carbons, we use the prefix eth. If it's 3 carbons, we use the prefix prop. 4 carbons, we use the prefix bute. It is bute, not but. 5 carbons, we use the prefix pent, like pentagon. 6 carbons, we use the prefix, you would think 6 carbons, you can probably guess is hex. 7 carbons is not sept, it's hept. 8 carbons, no, 9 carbons, 10 carbons. 8 is oct, 9 is non, 10 is dec. So as we make chains, we may have pentane, butane, propane, heptane, octane, nonane, decane. We can even add enes, octene, propine, butine, decane, methane. There's nothing for things to double or triple bond to a meth. So that'll usually always be ane. But here are these prefixes as they're part of a chain. You should have 10 note cards. 1, 2, 3. I was just being lazy without doing 10 separate boxes. So that is our little aside from the hydrocarbon functional groups. We're now going to get into some of the more standard functional groups. Not that those aren't, but the main ones that students generally have trouble naming, starting with alcohols. Alcohols we already hinted at. This is what we refer to as the hydroxy or hydroxyl functional group. So hydroxy or hydroxyl functional group. It is usually represented by carbon chain bonded to an oxygen and a hydrogen. The R stands for a carbon chain or hydrocarbon chain. So it could just be 1 carbon, it could be 5 carbons, it could be whatever. We generally use R to refer to some general amount. With that said, let's go ahead and make our note card. So on one side, I'm going to put what we just have, ROH. On the other side, I'm going to call it alcohol. With alcohol, we have a suffix, ol, OL. So for each of these, I'm also going to give you an example. So in this case, I'm going to use a skeletal formula. OH. This is F because we have 2 carbons, 1, 2. They're single bonded, so I'm going to say ethan because there's only single bonds. And then all, the suffix. So it all comes together here. So one more time, F refers to 2 carbons. An comes from the ane referring to the single bond here. All refers to the hydroxy functional group. That is ethanol. So that is alcohols. Moving on, we have aldehydes. And I apologize for this very long video that it will be. You may want to pause and start multiple times. So this is part of the carbonyl functional group. The carbonyl functional group is denoted by carbon double bonded to oxygen. Now, in an aldehyde, this is located at the terminal point. That means at the end of a chain, ends. So not the middle of a chain, the end of a chain. I'm just going to jump straight into the note card. So this is going to look like R, single bond to a carbon, double bond to an oxygen, single bond to a hydrogen. Again, that is aldehyde. And the suffix we use is al, A-L. So alcohol was O-L, aldehyde is A-L. Now, to do an example, we'll start with the simplest one, which is carbon double bonded to an oxygen, single bond to a hydrogen, and the R group being one other hydrogen. Being one carbon, this is going to be meth, single bonds between any carbon and other carbons, which there are none, and al, methanal. Moving on to a similar type, we have ketones. Ketones, oops, and I've already messed it up. Ketones don't have a Y, and I am known to always put a Y in my ketones. And that is also a carbonyl group. So, carbonyl functional group. Now, the difference between this is in the middle of a chain. So, in this case, going straight into our note card, we have R bonded to C, double bond O, bonded to R prime. I'm using prime to denote a different hydrocarbon chain. It can be the same, but it can also be different. We use the suffix "-one". It's spelled one, but it is pronounced "own". Make sure that you don't mispronounce it. If you're saying it out loud, it sounds weird. Any chemist worth their salt will use the term "own". Now, an example, because this is in the middle, we must have at least two other carbons. So I will draw the simplest one. And I'm going to use the skeletal formula. This is prop, because there are three carbons, and because they're all double bonded to each other, or single bonded, own, propanone. And it is our simplest ketone. Moving on, we have carboxylic acids. Carboxylic acids are interesting. They are the carboxyl functional group, and carboxyl is actually a combo. It is a combo of hydroxyl and carbonyl. So it brings those two together. In our diagram, we have R bonded to a C, double bond O, the carbonyl, single bond OH, the hydroxyl. And this is our carboxylic acid. Now, carboxylic acid has a suffix as well. It's oic acid. So, an example might be if we do a two carbon chain, this is F and oic acid, ethanoic acid. Ethane because of the two carbons, one here, and for the single bond, oic acid for the double bond O, single bond OH. Moving on, we can go to our esters. Esters are actually quite known for taste and smell, usually um, very often used in artificial flavors and perfumes. And this is actually a carbonyl with another oxygen in the middle of two carbon chains. So it's a little bit of a weird one, and students sometimes have trouble with this one. It is R, and here's our carbonyl group attached to an oxygen attached to another carbon chain. This is our ester. And ester has the suffix -ate. It's a little weird, and I'll show you how we use it. It's going to bring in a couple new concepts we haven't learned yet, and we'll explain further in another video, but right now it's a bit of an introduction. So I'm using the skeletal formula. You'll notice we have 1, 2, 3, 4 carbons, but this isn't actually referred to as bute. We look at the chain with the carbonyl group, and this is 1, 2 carbons. So we're going to name that first. That's actually going to be ethanoate using the -ate prefix. So ethanoate, and I'm going to go ahead and highlight that, and that refers to this with this functional group and that oxygen. Now, attached to ethanoate, we have another 2 carbon group. And so we actually use the term ethyl ethanoate. So we take our eth and we add the little YL to tell us that it's a chain attached to the what we call parent chain. And we'll learn about that a little more as we cover naming these compounds. That yellow is horrendous. Let me pick a different color that's a little more contrasting. So ethyl ethanoate. We add the -ate once again to the thing with the carbonyl group, and the ethyl refers to the chain attached. So esters are a little weird. Moving on to other weird ones, we're going to go to ethers. Ethers, getting the name from ether, what was commonly used as an anesthetic in early surgery and medicine. This uses what we call the alkoxy functional group. This is oxygen bonded to 2 alkyl groups. And an alkyl group is just going to be a chain of hydrocarbons. Something you may even note if you're looking at language is I say alkyl, similar to ethyl right here. So it gives you a little hint of what we're to see. We're to see some chains of hydrocarbons attached to our main thing, which in this case is actually the oxygen. So if we look at it on our flashcard, we have R bonded to O bonded to R prime. So once again, this is our ether. And ethers have a kind of in between. I'm not an English teacher. I don't know what this is called. Oxy. It goes in between our 2 chains in the word. So it's not a prefix, it's not a suffix, it's somewhere in the middle. I'm sure there's someone who's better at English that can tell me what that is. But an example, we could just look at ethoxyethane, which is what's commonly known as ether, but it doesn't really show what I'd like to show. And so I'm going to go ahead and this time draw the full structural formula. So I like to do all the formulas often just to ensure that we are understanding where parts are coming from. This one we call methoxyethane. Methoxyethane. So we see that the meth refers to this one carbon. The oxy refers to the oxygen, and the ethane refers to this two carbon chain. Now, of course, if this had a double bond, this might be methoxyethene. If it was a triple bond, it would be methoxyethine. So that's how we can start applying different groups coming together. We just modify the word of what we're using or the name. So moving on from ethers, we have amines. Now, amines, you might reference them from amino acids, which are proteins. Amino acids, funnily enough, use both an amine group and a carboxylic acid, which is where it gets its name. But an amine uses the amino functional group. You may also know that from ammonia. This is nitrogen bonded to hydrogen or other alkyl groups. This is a derivative of ammonia, where the name comes from. You should know ammonia being NH3 by now. If we go ahead and look at our flashcard that we're going to make, this is RNH2. This is our amine, and it has a suffix. It's very easy, amine. The suffix for amines is amine. I'll show you what I mean. In our example, we might just do CH3NH2, and this is methanamine. Simply put, we just add amine to the end of the word. On that same vein, we have amines, but we also have amides or amides. Sometimes people pronounce it differently just to make it easier to understand. I say amide, but I know others say amides, and it's amido functional group. And basically what that means is we have a carbonyl bonded to amino. So it's exactly what it sounds like. We have R bonded to C, double bond O, single bond NH2. Very similar to our carboxylic acid, but with an amine. This is amido. Similarly, its suffix is pretty easy, amide. Or we can say it's an amide, suffix amide. For an example, instead of doing meth, let's do eth. So double bond O, single bond NH2. This is ethan amide with a D, amide. All right, we got two more left and then we are done. Whoops. These ones are quite fun. Halogenoalkanes. Exactly what the name suggests. This is going to have a halogen bonded where a hydrogen would be. So we often represent this with an X. Whoops. I said an X and I wrote an H, where that X is any halogen. X is equal to Cl, F, I, or Br. And so it can be any of those. The name is halogenoalkane. And we have four different prefixes. The prefixes can be bromo, fluoro, fluoro, or iodo. And so the prefix changes depending on the halogen that you have bonded. So for example, if we just take methane, CH3, and we add an I, this would be iodomethane. But CH3 with an F would be fluoromethane, and et cetera, with bromo and chloromethane. So we just use whichever halogen is attached. Now, the last one, and I'm going to move all the way over to a new page, is called arenes. Arenes are what we refer to as aromatic hydrocarbons, meaning you can smell them. This is part of the phenyl functional group. And what phenyl basically refers to is a benzene ring. Benzene ring. Now, if you remember benzene is 6 carbons with double bonds and a hydrogen on each, often referred to with the circle. And if you remember, that circle is the delocalized electrons that occur in these double bonds, both above and below the plane. Now, what we mean when we have a functional group of this, and we'll draw it right here. We'll do both drawings actually. R bonded to our benzene ring. And by both drawings, I mean both representations of benzene. You may see both in your DP exam. So it can be either or. And this is our arene. Our arene is referred to as phenyl prefix. Now, a very common example would actually be what we refer to as phenol, OL. If you think about that for a moment, OL comes from the prefix of hydroxy. So this would be phenol. So we replace our R group with the hydroxy, and then we get phenol with an OL in the back. So we're going to go over how to name all of these, but for you to be able to name larger and more complex chemical compounds, you need to have these memorized. So my advice one more time is go through, make sure you have all these flashcards made and start memorizing them. It takes a while. Bring them wherever you go. If you have time, instead of scrolling the internet, Instagram, whatever, you are instead doing flashcards, memorizing your organic chemistry. It is definitely not something that's super fun or super easy, but it will be an invaluable resource as you move through the DP chemistry, organic chemistry curriculum, as well as if you ever have OChem moving into college. Anyways, I hope this helps and have a great day.